Welcome to Hershey Park Arena, located in Pennsylvania, USA. The arena roof was designed by Anton Tedesko, who is credited for bringing the German tradition of vaulted forms to the United States. Learning about Tedesko and some of his major works is one of our learning objectives. In addition, I'm going to describe classical forms for vaulted shell structures, such as domes and barrels. And finally, I'll end the lecture with some examples of the importance of the form of a vault, meaning the shape of the vault. Before we get into 3D vaulted behavior, let's examine the 2D behavior of an arch. The 2D behavior of an arch is not the same as the 3D response of a vault, but it will help us to move our thoughts in that direction. What is the ideal form for a concrete arch? Well, if we hang weights from a string, we get pure tension in that string. If we can freeze it and turn it over, we get pure compression, which is perfect for concrete because concrete has almost no strength in tension. If the load is uniform, the shape is essentially a parabola. But if the load is not symmetrical due to trucks on a bridge or wind on an arched roof, the arch cannot adjust the shape like a string can. The arch will deflect, and in this sketch, the dashed line is the original form and the solid line is a deflected shape. This creates bending stresses in the structure, something that we want to avoid in thin concrete vaults in particular, since it does not have much strength in bending. The most efficient way to carry loads in concrete vaults is through pure compression. To reduce and/or control the bending stresses in arches, we can introduce what are called hinges. A hinge is defined as part of the structure that does not resist rotation. Think of a hinge on a door. That hinge will allow the door to swing freely without any resistance to rotation. Bridges are often designed with hinges. For example, Robert Mayar's Saginaw-Tobel Bridge is a 3-hinged arch bridge. This concept of 3-hinged arches can be extended to long-spanning roofs. It was applied as early as 1889 for Machinery Hall in the Paris Expo. Now let's apply this very general idea of arches to domes. A spherical dome is the simplest type of dome, but it is not the ideal shape of an arch, meaning a dome is spherical or circular. It is not parabolic. The loads in a spherical dome are carried by meridians and hoops. The meridians can be thought of essentially as arches. It carries the gravity loads to the supports. But the loads in a dome are transferred to the supports much more efficiently than a series of 2D arches due to the 3D effects of the hoops, which interact with the meridians, tie them together, and keep them from bending. We've begun our scientific study of vaults through domes. We started to look at hoops and meridians. I'm going to continue explaining the stresses in the hoops and meridians in a moment, and then continue with a study of Franz Dischinger, who published the first mathematical formulation for domes in 1928. A year later, he designed the Leipzig Market Hall in 1929, and I will go over that structure as well. Going back to meridians and hoops, notice in the sketch the dashed lines. Below the 52-degree mark, we have tension in the hoops, which can lead to cracking in the concrete. The meridians are always in compression, hence the lines are always drawn solid. The hoops go into tension as you go down towards the support. They're in compression towards the top of the dome and then transfer into tension below that 52-degree mark. In ancient times, this was not fully understood. The Pantheon, for example, is the oldest major concrete structure. It's a hemispherical dome, and it's coffered, meaning you see these square indentations inside of the dome, and that makes the dome lighter. The dome of the Pantheon spans about 43 meters, and it was built in the 2nd century. Pictures taken by David Billington many years ago clearly show the cracks in locations below 52 degrees. I visited recently, and although the cracks aren't as clear as they were many years ago, they are still there if you look for them. Concrete vaults today have steel bars embedded in the concrete to enable the structure to carry a mild amount of tension. This is called reinforced concrete design, that is, concrete reinforced with steel. The Pantheon does not have steel reinforcement, so it can be assumed that these cracks were there from the beginning. The Romans probably saw the cracks develop and consequently loaded the sides of the dome near the supports with more stones and concrete to eliminate some of that tension. To understand the meaning of this, take a piece of string and load it uniformly with weights. That is, weights of equal amounts and equal distances. The form is essentially a parabola, as I noted earlier. If you want the shape of that string to take the form of a circle, you'll need to load more heavily the edges near the support. Flip this physical concept to understand the concept of circular arches and domes. If we look at a cross-section of the Pantheon, you'll notice that there are more weights, more concrete and stones on the outside near the supports compared to towards the center. Now let's trace the origins of modern reinforced concrete domes. This image is a dome in Breslau, Germany. Notice how the meridians and hoops are expressed as arches and rings. It isn't really acting as a 3D reinforced concrete thin shell vault in its purest meaning. In comparison to a slightly larger dome in Leipzig, Germany, this table shows that Breslau weighs about 3 times more. And the dome of St. Peter's in Rome weighs about 5 times more than the dome of Leipzig. Here's an image of Leipzig Market Hall in Germany, and it was designed by Franz Dischinger in 1929, 1 year after he developed the mathematical equations that define the dome. The Leipzig market halls were perhaps the first modern reinforced concrete thin shell or vaulted dome, and they begin the German tradition. They're about 4 inches thick, and they're polygonal. They have 8 sides. The shape is close to a circle, close to a spherical dome, but not exactly. The major difference between Leipzig and Breslau is that Breslau is conceived of as a series of arches and rings supporting a roof, whereas Leipzig is a self-supporting thin shell roof stiffened at its polygonal folds by thin ribs. A modern view of Leipzig shows that it's still standing in good condition today. If you would like to know more about Leipzig, a group of students at Princeton made a study of these shells, and their scientific, social, and symbolic analyses are described in a website called shells.princeton.edu. The designer of Leipzig, Franz Dischinger, recognized that there were few opportunities for spaces with circular floor plans. A more practical use of vaulted forms was one that covered rectangular spaces. He made an experiment of a rectangular floor plan dome. This is a square plan with rigid boundary conditions which follow the mathematical formulation. And it's a demonstration of strength by loading it with engineers. Now we're going to move to the scientific analysis of another very common geometric form for vaults called barrels. Barrels are essentially slices of cylinders. The person who published the mathematical formulation for barrels was Ulrich Finsterwalder, and he does this in 1933. Generally speaking, the behavior of barrels falls into 2 categories. There's the long barrel and the short barrel. In a short barrel, the length L is small in comparison to the radius of curvature of that barrel, and therefore this barrel will behave essentially like an arch. The forces flow down to the edges where it's carried to the supports. In a long barrel, the length L is relatively large, and therefore it behaves essentially like a beam, with compression on the top of the shell and tension towards the bottom. This is a very simple way of looking at barrel analysis. Of course, a more refined examination requires higher order mathematics. In the left is a paper by Finsterwalder with the handwritten notes of Félix Candela, whom we'll study later. Even the simplest of shells requires significant mathematics like 8th order partial differential equations, as seen on the right. These formulas assume a boundary condition, that is, a certain behavior at the edges and at the supports. The Germans constructed their vaults so that the boundary condition matched the assumptions of the formula, which makes sense, especially since these very thin vaults of reinforced concrete were an innovation and they were being as cautious as possible. For Finsterwalder and Dischinger, the form follows the formula. The one who starts to break away from this is another engineer, Anton Tedesko, whom we'll study next.